Any questions at all before we get into the stuff or continue, I should say, with the stuff we were talking about last time with kernel and range of transformations? All right, so this is the example we were working on last time where we had asked whether or not this particular vector was in the range and said that we could, pardon me, figure out if it's in the range or not by trying to solve the equation t of x equals that particular vector. So remember again, range is a set of all possible outputs. So if we treat it like it's an output and solve, we should say, okay, can we solve it? In this case, we could. There were lots of different vectors, bless you, lots of different vectors that'll map to 1, -4. We just picked one to show that it was in the range. Let's equal 0. We got that. We really did find that vector was in there. If we put the vector 5, 0 in there instead of the 1, -4, that was the second question that it asked, is 5, 0 in there? If we set up the same type of system of equations, literally the same set of equations, except that I'll use 5 and 0 for the constants. If you try to go through this row reduction, yes, we did what? Yes, we did. Would you like that? You're welcome. Well, notice again, we noticed that this second row here is -4 times that first row if I ignore the constant terms. So if I take 4 times the first row and add it to the second row, you'll get 0, 0, and 20 here, right? What does that tell you about the system? It's inconsistent, right? There isn't a solution. So what would you say about that vector? Is the vector 5, 0 in the range? No. Okay. So again, when you're trying to show that something is in the range or to show that something's not in the range, you're really talking about, again, solving a system of equations and seeing whether or not that system is consistent or not. In this case, in the second example there, it's not consistent, so that vector will not be in the range. Okay. The first example, it was consistent, so the vector is in the range. So the last part says, can we find a basis for the range? What do you think that answer is? Yes or no? Well, notice I ask it again for the next example, so the answer is probably yes. Okay, so let's think about it again. Range is set of all possible outputs, right? That's what range means. Put absolutely everything in that you have in your domain, every output that you possibly get, that's the range, right? So instead of everything that gets hit, if you will, by the function, right? Okay. In this case, how have we represented the transformation? Well, we've represented it as matrix multiplication, haven't we? Right? So we're looking for, as far as the range goes, we think about it in terms of matrix multiplication. In this particular example, we'll notice that the outputs that come out are two-dimensional vectors. So those will be all of your, well, let's just write it this way. It's the set of all outputs or set of all matrix multiplications that we can do here. Again, we use that brackets around the T to denote the standard matrix of the transformation. That's what we mean by the range, right? It's every possible output that you can get by putting things in the domain and doing the transformation. In this case, again, we can recognize that the transformation is matrix multiplication, so we can get the range that way. Well, when we do this multiplication, pardon me, let's think about what we get as we multiply this stuff. So if, for example, you were to do, well, I'll just write it this way, just generally speaking. If you had a column here and a column here, so on down the line, let's say we had n columns, and then multiplied by an x1, x2, down to xn, how could I write the answer? What does this x1 always get multiplied by? And the x2 always gets multiplied by c2 and all the way down, right? So the answer, if I write it in a vector notation, looks like x1 c1 plus x2 c2 all the way out to xn cn, right? Or a linear combination of the c's. Agreed? What kind of a thing do we have here then? We call that what of the c's? A linear combination, right? Now again, remember we're doing this for all possible x1s out to xn's. So this is a set of all possible linear combination of the c's. What space associated with a matrix is a set of all linear combination of the c's? Span of what? The columns. So the span of the columns is called the, I think you just said a second. This is column space, right? That's the column space of the matrix, correct? Right? So notice that your range of the transformation corresponds to exactly the column space of the matrix of the transformation. Exactly what it is. How did we find the base? How did we find a basis for your column space? It was just on your last test. How'd you find a basis for the column space? Yeah, right. Well, reduce and find pivots, right? Figure out where the pivots are, and then the columns that correspond to the pivots give you your basis, right? In this case, when you row reduce, I already did that here, didn't I? If I ignore this column here, this is the reduced row echelon form of the matrix that we found, right? So what would you use for a basis? Well, the 2, -8 part, right? Apparently, it also made it disappear when I just did that. It's gone now. Okay. All right. So we would go back to here. So a basis for the range would be the vector. I'll write it as a vector this way, 2, -8. So what that means is that any multiple of the 2, -8 would work. Notice that 1, -4 is exactly a multiple of that, right? If I do half of that. So anything that's a multiple of this will be in the range. But this is how you find a basis for the range. You look at the same idea that we did with the matrix. Well, when we have, I should say this is how we work with finding a basis for the range when we have a matrix associated with the transformation, and we can go back and just do the basis of the column space like we always have. Okay. All right, let's do the next one here. Same questions. This particular transformation is going from R4 to R3. So again, if we set up the standard matrix for this transformation, what size will the standard matrix have? It goes from R4 to R3. The matrix has size 3 by 4. Remember, it flips it around. Yeah. Okay. So we'll have a 3 by 4 matrix. How do we fill out the entries in that matrix? Yep, so yeah, we use the coefficients there for the W, X, Y, and Z, right? And write them as, I would put them in the matrix as the rows, right? So do 4, 1, -2, -3 for the first row, 2, 1, 1, -4 for the second row, 6, 0, -9, 9 for the third row. right? Okay. We'll do the basis questions here in a second, but let's remember what each of these questions is asking. The first part asks, is the vector in the kernel? How do you get in the kernel? What does it mean to be in the kernel? You plug it in, you get exactly what? There's a specific thing you get when you plug it in. Zero, right? You plug it in, you get 0, right? So if I take this as a column and multiply together, we should get 0 if it is in the kernel. If it's not 0, then it's not in the kernel, right? So if I take this t and multiply it by 0, negative 4, 1, 0 as a column, we get 4 times 0, 1 times negative 4 is negative 4, and then we get a negative 2 times what is negative 2, negative 3 times 0 is 0. So we end up with what, a negative 6 in the first component? Does it matter what's in the next ones? No. This is certainly not the 0 vector. So 0, negative 4, 1, 0 is not in the kernel. I did the matrix multiplication. You could have just as easily put in 0, negative 4, 1, 0 in for W, X, Y, and Z. They got a negative 6 here at that point and said it's also not in the kernel, right? I could have done it either way. Directly plug it in, see that you don't get the 0 vector, or do the matrix multiplication and see that you don't get the 0 vector either way. That makes sense? If we want to show it's in the range, what do we do? Yeah, row reduce and see if it's consistent or not, right? Okay. So I put in 4, 2, 6, 1, 1, 0, negative 2, 1, negative 9, negative 3, negative 4, 9, and 1, 3, 0. And put that in reduced row echelon form. Let's do that real quick. I'm going to write this on the board so that I don't have to keep flipping back and forth between things to remember what the matrix is. So I type it in here. So let me open up R because that's the easiest thing for me to get on the computer here to get it to row reduce. I would expect that you'd probably put this in your calculator. Let's I could type, this would be very much pretty helpful. And then let's row bind. Oops, let's make it. I'll give it a name. 4, 1, negative 2, negative 3, 1, 2, 1, 1, negative 4, 3, and 6, 0, negative 9, 9. Sounds like you were cracking open a cold one. I'm sorry, I'm going to need something stronger if I'm going to get through the rest of this class. All right. There we go. Let me move that up a little bit so we can actually see it. Is that consistent? It's going to be consistent. You're looking for a pivot in every row, right? You get a pivot in every row here? Or at least a pivot in the rows where there's non-zero pivot in the rows here. So notice this will be consistent no matter what you plug in, but you could also have a row of zeros at the bottom. As long as it's a whole row of zeros, it will still be consistent, right? But in this case, no matter what I would plug in on the right-hand side, it's going to be consistent because when we do the reduced row echelon form, we get a pivot in every row. Again, here, if I want to look for something specific then that maps to the vector that I'm interested in, I could just make 0 for that variable, right? That's free. I can make that 0. That would say that your W would be -3/2, your X would be 10, and your Z would be 1. Right? So I'll write that on the board, but I'll say it again. So looking at the third column, that's free. You can make it anything. I'm going to make it 0, so I don't need it, right? So your Y will be 0. If your Y is 0, then your W is -3/2, your X is 10, and your Z is 1. And then you could check that when you do the transformation applied to that vector, you really do get the vector 1, 3, 0. So again, you should check that T of -3/2, 10, 0, 1 is 1, 3, 0 in that case. And again, there was actually nothing special in this case about the vector 1, 3, 0. So as we look at the reduced row echelon form here, when we look at the reduced row echelon form here, I can always solve it no matter what's over here. Right? Agreed? Doesn't matter. So your column space of, again, ignore the constants. The column space of your matrix is going to be what? If I get a pivot in every row, that tells me that we span, right? Okay. So the column space is going to be all of R3, right? Because the columns are in R3, right? So if you want a basis for the range, you can just use a basis for R3 in this case. A basis might as well you did. Might as well you use, and you can just have all of R3. Yeah, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? I can use that particular basis in that case, right? All right. So going back, flipping back over. This was, I don't remember what the reduced row echelon form was because it was on the board, but whatever. It was on R. Anyway, doesn't matter. You have that. Should have you in your notes now. But a basis for the range, you can just use your standard basis. You could have also just used the original columns that corresponded to the pivots, right? You could have also used 4, 2, 6, 1, 1, 0, -3, -4, 9. Those have been the columns that have corresponded to the pivots, right? It was the Y column that didn't have a pivot, right? Okay. Either works. Doesn't matter. In particular, the reason why it doesn't matter is that we're just looking for a basis for the whole space because the whole space, the whole codomain, is your column space. We refer to that as being onto, right? Onto means that everything in the codomain gets hit. All right, let's go back to basis for your kernel. I'll flip back over to the reduced row echelon form here real quick since I forgot what it was. If you're looking for a basis for the kernel, again, imagine that we have zeros now over here in column 5. I don't need to redo the reduced row echelon form, right? Just imagine there are zeros here. I've got free variable here, right? So your Y is free. So say that's equal to T. Well, again, if we have zeros in the rightmost column, what's the Z going to equal? We've got zeros in that last column. What's the Z going to equal? 0, right? Because notice that this literally says Z would equal 0 here in that last row, right? What would your X equal? Looking at the second row again, where this 10 is, would be a 0. You'd probably -4t, right? And then finally, what would your W equal? 1.5t or 3/2 t, right? Agreed? Just moving that over to the other side. So again, if we factor out the t, that should give us the basis that we want for the kernel. This is why I typically use the chalk holder. If we factor out the t, what can you use for a basis for your kernel? Good. That'll be a basis for our kernel there, right? Again, remember t can be anything, so essentially this is just any multiple of this vector would be in the kernel. Is that okay? Any questions on that particular example before we go on to the next one? Lots of new words and new ideas, but all connecting back to systems of equations again. Let's see if we can extend that idea. Our next example here has a transformation that goes from degree 3 or less polynomials to degree 2 or less polynomials. The notation here says you're going to take the derivative and then plug in 2x minus 1. Okay? That's what the notation says. It says find a basis for the kernel and the range. And it also gives you this little hint of use the standard bases for P3 and P2. So let's talk about what that means in that particular instance. Why does it tell us what to do? Well, let's first just apply the transformation to the basis. So what is the standard basis for P3 again? Right in this order. Yep. And 1, right? That's our standard basis, right? Usually we write it in ascending order. Doesn't really matter, but that's usually how we write it is ascending order. Do the constant, the x squared, the x cubed, all right? Let's apply the transformation to the standard basis vectors. Remember again, the notation says take the derivative and then plug in 2x minus 1. The derivative of 1 is 0, plug in 2x minus 1, you still get 0, right? Take the derivative of x, what do you get? 1. Plug in 2x minus 1, you still get 1, right? Because remember, the notation means take the derivative and then plug in 2x minus 1. Plug in 2x minus 1 into the derivative. That's what the notation means, right? Derivative of x squared is 2x, so this will be 2 times 2x minus 1, or 4x minus 2. Right? And then finally, derivative of x cubed is 3x squared. So we'll plug in 2x minus 1 into 3x, into x, try that again. 2x minus 1 into the 3x squared. If we distribute everything out, looks like we get 12x squared minus 12x plus 1, or plus 3, I mean. That's okay. All right. Now again, remember, once we know what a transformation does to a basis, we know what it does to absolutely everything, right? Because I can write any polynomial here as a linear combination of the standard basis vectors, right? So for example, if you wanted to do, say, the transformation applied to 3 minus x plus 2x squared plus x cubed. I can break this up over the sums and differences and pull out the constants, right? That's the whole point of doing it on the basis. This would be 3 times the transformation applied to 1 minus the transformation applied to x plus 2 times the transformation applied to x squared plus the transformation applied to x cubed. We already did all these other pieces here. So I can plug in the 0 for t of 1. That just gives me 0. Plug in the 1 for t of x. Plug in 4x minus 2 for t of x squared. And plug in the 12x squared minus 12x plus 3 for the t of x cubed. And rearrange here. You get 12x squared. What is that? Minus 12 plus 8 is minus 4x. Minus 4 plus 3 is minus 1. What's that? Oh. I did my arithmetic correctly. Oh, sorry, I forgot the extra minus 1, didn't I? Oh, here. I forgot the minus 1 there. It should be a minus 2. We got minus 4 plus 3 is minus 1 minus that extra 1. I forgot the one that was sticking up front. You could have also done it directly, right? You could have just taken the derivative and plugged in 2x minus 1. You should get the same answer. Better get the same answer. Otherwise, something is seriously wrong. Okay. So far, so good? Okay with that? Okay. So, in general, if you were going to do this, if you had some a plus bx plus cx squared plus dx cubed, I could do the exact same thing, right? Pull out the a, pull out the b, pull out the c, pull out the d, right? And get the exact same thing, right? So notice again that everything here is determined by where it sends 1, where it sends x, where it sends x squared, where it sends x cubed. Okay. But let's see if we can take this a little bit further. We've talked about this before. We said that when we've got polynomials, really there's kind of a correspondence between polynomials and the n, wherever the n is the number of coefficients you have, right? There's some sort of a correspondence between P3 and R4. Because I can think of the 1, the x squared, and the x cubed just as components, right? Because all we're ever doing is scalar multiplication and adding, right? When you add coefficients, you're adding basically the terms that are in the same component, right? So you really think of this as doing the same thing with real numbers, or sorry, real Euclidean vectors, I mean. And we can use our knowledge of that to help us write a matrix for this transformation in terms of the basis, okay? Because again, we can think of this as being the vector 0, 0, 0 in P2, can't we? Right? We can think of this as being the vector 1, 0, 0 in P2, right? This one being the vector, what? What would this be in P2? It'd be negative 2, 4, 0, right? And this one would be good again, 3, negative 12, 12, right? Sorry. Apparently Siri doesn't want to learn linear this morning either. All right, so I can think about that in terms of those particular coordinates, if you will, right? Then we're going to extend this notion to when we have bases that aren't the standard bases as well, and still be able to convert it to a matrix. That's later on. But let's do this one in this particular case. So notice that these are the outputs, right? In terms of these things. So in each of these, you would do A times that plus B times that plus C times that plus D times that to get your answer, right? Notice when you add those, you would add your components. You would have A times 0 plus B times 1 plus C times -2 plus 3 times, or D times the 3 in the first component. You would have A times 0, B times 0, C times 4, D times -12 in the second component. And now it starts looking like the format of those transformations that we just did. We're going from Rn to Rm, right? We agree? Okay. When we did those, we wrote those as rows across. We picked up the coefficients. But notice we could have also thought it the other way and thought we had, looking back up here, notice in this one, we had a 4, a 2, and a 6 on the W's. That's your first column, isn't it? Notice that would also be the output if I plugged in the vector 1, 0, 0, 0. That would be the output, wouldn't it? Notice in the second one, we've got 1, 1, 0, which is that column. That would be the output if you put in 0, 1, 0, 0, and so on up the line. Okay? So when I create this matrix, when I've got coordinates, I could do the matrix for T in this example by taking our image of our standard basis vectors and putting them in as columns in our matrix. Now, something to notice here, we're going to go here from P3 to P2. That's like dimension, that's like R4 to R3 or dimension 4 to dimension 3. What size matrix do we have? 3 by 4 again, right? Looks like it reverses those ideas, if you will. Cool. So this would be the matrix of this transformation. Okay. If you wanted to know the output, so notice this is all in terms of the standard basis. If I wanted an output, I did this example a minute ago, right? Okay. Let's say I do this matrix and multiply it by the 3, -1, 2, 1. What do we get? 0 times 3, 1 times -1, that's -1. -2 times 2 is -5, plus 3 gives me -2. Right? Do the next one, 0 times 3, 0 times -1. 4 times 2 is 8. -12 times 1 is -12. 8 minus 12 is -4. Finally, the only thing we get down here is 12 times 1 when we do that product, isn't it? What in P2, what would -2, -4, 12 correspond to? So let's think about what we just did here, by the way. We just did differentiation and a function composition through matrix multiplication. I'll say it again. We just took a derivative and a function composition combined through matrix multiplication. That's kind of cool. Yes.
Where did the A, B, C, and D values come from?
These?
Yes, those.
This would just be what an arbitrary polynomial looks like in P3. No, there's no calculation you missed. That's where those are the arbitrary ones, which is why I was saying that all of these things just correspond to our standard basis vectors. And then I can look at what the outputs of the standard basis vectors were to create our matrix. That was the idea. All right, anyway, so let's look at this particular matrix here. The problem asks you for what's the basis for the kernel and what's the basis for the range. That's what the problem asks for, right? Now I've got it set up as a matrix. What do you think we should do with that matrix? Answer those again. Or row reduce it, right? That's going to answer both those questions, correct? Well, when we row reduce it, notice it's quasi-triangular here already, right? I'm going to get a pivot in column 2. I'll get a pivot in column 3. I'll get a pivot in column 4, right? In particular, I get a pivot in every row. What does that tell me about the range if I get a pivot in every row? Yeah, it's it's all of the codomain, right? So my range here will be all of P2. So I can just use the standard basis for P2, right? For the range, you can use the standard basis, or you can just pick out the columns that correspond to pivots. Either one works, right? Okay. But a basis for the range here will be 1x squared, because it's onto. How about a basis for the kernel? Well, when you do, what did we just say if we row reduce this? What's going to happen in column 2? What are we going to get if we row reduce? Pivot, right? What are we going to get here? Pivot. What are we going to get here? Pivot. So the only free variable is the first column. What would all the other variables have to be if you said that equal to 0? If I get a pivot in the column 2, and a pivot in column 3, and a pivot in column 4, what would that say if I put zeros here on the right-hand side? That would tell me that that would equal, well, these will go away, right? If I get a pivot here, all of these will go away, right? I'll get 1, 1, 1, 0, 0, 0, right? So that'll tell me that equals 0, yeah. This equals 0, this equals 0, right? So let's contextualize it. Is x in the kernel? If it says that I have to get x, to get something times x to be 0, what do we have to use for the constant? 0. So is x in the kernel? No. Right? And think about it from a practical standpoint. What do you get when you differentiate x? 1. And if I plug in 2x minus 1, we get 1. Is that 0? No. So x isn't in the kernel. Let's contextualize the next one. This would say that if I have a something times x squared is 0, what does the something have to be? 0. So x squared is not in the kernel either, right? This would say that if I have something times x cubed to give me 0, I had to use 0. Again, so that tells me x cubed is in the kernel. So in this case, from a matrix standpoint, we'd have that the basis, if I think about it as a matrix, the basis for the kernel would be 1, 0, 0, 0. But if I think about it, if I contextualize it back to what we have, what does that vector correspond to? What does 1, 0, 0, 0 correspond to back in P3? 1. Now let's think about what you know about calculus. What functions have derivative 0? Constants. What do we just generate with that basis? Constants. So again, contextualizing it, hopefully that makes sense. So the kernel here has to be just the constant terms. If I have something that's not constant when I take a derivative, it's not going to be 0 all the time. It could equal 0 at some point. But when we say it's not 0, we mean it's not the 0 polynomial, not that it's never equal to 0. Okay. It means it's not identically 0. It's not the 0 polynomial. Okay. We're going to come back to this notion. This is not the only example we're going to do of this, okay? But that's the idea behind this, is to try to change linear transformations, whatever the function might give you, into matrix multiplication. That's our goal. Okay. All right, let's do a couple of definitions here. Remember what it means to be one-to-one? Just in functions in general? If I have algebraically, if something is one-to-one, what does that mean? Yeah, there's only one output, and if I put in different inputs, I get different outputs, right? That's what one-to-one means. So usually we write that as if I got the same thing out, then we must have put the same thing in. Conversely, the contrapositive would mean if I put different things in, got different things out. But this is typically what we use to show that functions are one-to-one. So the theorem here just translates one-to-one into the language of transformations and kernels. It says that if it's one-to-one, it says that the transformation is one-to-one if and only if the kernel is 0. All right, let's do this proof here. Let's suppose t is 1-to-1. Oops. All right, so the first thing I'm doing here is where does the transformation map the 0 vector? Well, we've done this trick a few times before where we've just rewritten 0 as 0 plus 0. The reason why we would do that in linear transformation speak is because what can I do with the transformation relative to this plus sign? Break it up. We can split it, right? Now what can we do on both sides? Subtract the transformation of 0, right? When we do that, we get 0 is equal to t of 0. For emphasis sake, I'm going to emphasize where those 0 vectors are. When I take the 0 vector from V and plug it into the transformation, I have to get the 0 vector for W out. This is always true, no matter what. Okay? Doesn't matter what the transformation is. When you plug the 0 vector in for the domain space, you get the 0 vector for the codomain space every time. Okay? So where does that tell you that the 0 vector for V lives? Oops. What does that have to be in? If I plug the 0 vector in and I get 0 out, where does that live? What space contains the set of everything that goes into 0? The kernel, yeah. So this tells me that this has to be in the kernel. What are we assuming about t here? What kind of a thing is t besides being a transformation? It is 1-to-1. So is there anything else that can get mapped to 0? If it's 1-to-1, is there anything else that can get mapped to 0? No. So since t is 1-to-1, t of v is not 0 whenever v is not 0. Hence, the kernel is just the 0 vector. Okay, so that's one direction. If it's 1-to-1, we know that the 0 vector in V gets mapped to the 0 vector in W, so the 0 vector is in the kernel. If it's 1-to-1, that's the only thing allowed in the kernel. Let's go the other way. Let's suppose, or what I like to call suppose, that the kernel is the 0 vector, just the 0 vector. And this will be the 0 vector in W. Oh, sorry, the 0 vector in V, I mean, but I'm going to try to suppress the subscripts here so I don't have subscripts going everywhere. Again, this is a pretty typical proof technique in mathematics, or in algebra specifically, to show that a function is one-to-one. Suppose you have two outputs that are the same. If you're asked to prove something is one-to-one, you should never ever say, I don't know where to start. This is where you start. Okay? You may not know where to go from there, but you know where to start. Okay? Anytime you try to show something is one-to-one, algebraically, you're going to start with a statement like this. Okay? All right. We're given something about the kernel. How is the kernel defined again? It's a set of all vectors that get mapped to 0, the 0 vector, right? What can I do to this equation to get the 0 vector involved? I could add the 0 vector to both sides. What's another way to do it? So if I want to rearrange this equation so I see 0 on one side. Yeah, let's just subtract. That introduces the 0 vector, doesn't it? What can I do on the left-hand side? Say again?
Actually, they're equal.
The property of transformations. What can we do on the left-hand side? Yeah, this is T of V1 minus V2, right? Transformations break up over sums or differences, but they also, combine over that. Where does this tell me that V1 minus V2 lives? Where does it live? If I take the transformation and apply it to that vector, I get the 0 vector. Where does V1 minus V2 live? In the kernel. But what did we say the kernel is? Just the 0 vector, right? This is a statement about kernel, right? Transformation applied to the vector is the 0 vector. Yeah? Okay. So the V1 minus V2 is in the kernel. The kernel, though, is just the 0 vector. Hence, what does V1 minus V2 have to equal? 0, or they must be equal to each other. That's exactly what we wanted to show that the transformation is one-to-one. Let's see what's up. Okay. Let's try to see what was on the next page. All right, so this is, generally speaking, when you're looking at the kernel needing to be the 0 vector tells you it's one-to-one. Let's think about that in terms of the language of matrices just real fast. Kernel of the transformation is 0. Kernel is a set of everything that gets mapped to the 0 vector, or thinking of solutions to sets of homogeneous equations, systems of homogeneous equations, right? If we only want the trivial solution, that's what the kernel would be, right? The kernel being 0 would be. If we only want the trivial solution, what do you need to see in a reduced row echelon form? You need a pivot in every column for only seeing the trivial solution, right? So a transformation is going to be one-to-one if you can write a matrix for it, row reduce it, and see a pivot in every column. That'll tell you it's one-to-one. So what we'll talk about next time is the onto bit. Then we're going to do the onto bit. I bet you can figure out the reverse. We already talked about it a little bit. Instead of a pivot in every column, we'll be looking for a pivot in every row. So if it's one-to-one and onto, What matrix better you see when you row reduce? The identity matrix. I bet we're going to add something to our omega theorem towards the end here. All right. Have a good one. We'll see you on Wednesday.